Let's recall where we were, right? So for the past 2 lectures, we've set up a few of these models. In the first lecture, we kind of set up our entire framework. We looked at some ideas for information theoretic or statistical lower bounds. Our second lecture was focused mostly on algorithms or positive results for detection and weak recovery. The plan today is to kind of go beyond just weak recovery and say, okay, can we identify the best estimators in some sense? Can we do optimal recovery? And I'll make sense of this as I go along. That's where I'll focus most of my attention, and I think towards the end I'll talk a bit about statistical computational gaps. I think today's discussion will be sort of at a slightly higher level, and then depending on the interest we can see if we want to pursue this more in our next lecture. Okay. And as you will see from some of the references that I have, that this optimal recovery question is a more recent endeavor. So we are getting closer, I think, to the edge in some sense. Okay, so most of my discussion regarding this question of optimal recovery will be based on these like Gaussian spiked models, because this is mostly where we have had some recent progress. But I'll point to one other reference in the context of community detection. But okay, so recall that this is our Z2 synchronization model that we have been looking at. We have this vector sigma that's generated, coordinates are IID Rademacher, and then the matrix that we observe is a rank 1 spike plus noise. Right? That's our setup. And last lecture we looked at this question of weak recovery. What is weak recovery? I essentially, want to produce an estimator v hat, which is a function of the matrix that I observe, such that if I look at the normalized inner product between sigma and v hat, 1 over n, absolute value, I wanted this to be bigger than some epsilon with high probability. That's all that I wanted. And we saw that this is possible if and only if lambda is strictly bigger than 1. Okay, now comes the question. Once you understand this, you can say, okay, suppose I am in a regime where lambda is bigger than 1. I want to do better than just weak recovery, right? Can I produce an estimator that has the best possible correlation? Right? That's a natural question. And you would naturally expect that you should be able to do better than some of the estimators we have looked at. For example, one estimator that we have looked at quite a lot is the spectral estimator, which is just based on taking the largest eigenvector or the eigenvector corresponding to the largest eigenvalue. But the point is, this particular estimator, for example, doesn't really exploit the information that every coordinate of sigma is plus or minus 1. Right? So therefore, you believe that if you could have some other estimator that actually exploits this information, you would do better. And so the question mainly for us today is, can we do optimal weak recovery? Okay. So there are 2 comments in this context. One is, okay, how would we make sense of optimality in this context? And this is where the Bayesian formulation will be helpful. Okay. Given that this is a completely Bayesian problem, this is my unknown parameter, I can talk about optimal estimation, right? So we had one of these questions in our prior lectures, why do I assume a distribution on sigma? I could have as well assumed that sigma is just some unknown vector, maybe that is balanced, right? Up to weak recovery, you don't really care, but if you want to talk about optimal recovery, you need a bit more. Okay. That's one remark. And the second remark is, okay, so one Bayesian formulation helps to define optimality. The second point is that, okay, what is our notion of loss or performance, right? Let's say metric of performance. Right? And I can do it in a number of ways. One is, of course, to just look at this inner product. I need to look at the absolute value of the inner product because there is always this sign symmetry that's involved in the problem. Like, you can't distinguish between sigma and minus sigma based on your observation, right? So, for example, two candidate metrics, you can, given an estimator, you can measure its performance in terms of the correlation, let's say, v hat sigma square root n. This could be one metric. And then you could also look at some kind of squared error loss on the rank 1 matrix itself. So for example, the other idea is to look at a loss where if you had some estimator x hat, you look at the Frobenius norm square. This is a squared error loss for sigma sigma outer product. Okay.
So is this x just a 3 times 3 transfers?
Not necessarily. So I don't necessarily require here that x hat should be a rank 1 matrix. I just want some matrix that estimates this rank 1 matrix. And x hat is just a function of the matrix that I observe. Okay. Right. And so, to ground our discussion, we will need some kind of benchmark on the Bayes optimal performance itself, right? That's how we will compare the performance of specific estimators to the Bayes optimal performance. So I should tell you that this has been done. So the Bayes optimal performance is well known. So this is a result due to Deshpande, Abe, and Montanari. This is actually from 2016. So they essentially characterize what would be the Bayes optimal performance under a wide variety of metrics, including the two I have here. Just to state one of the results, for example, x hat Bayes. So if you look at the second squared error sort of metric, then this is nothing but the posterior expectation of this rank 1 matrix given your data. And if you define MMSE, this is the so-called mean square error, or the minimum mean square error, as 1 over n square, Frobenius norm of x hat Bayes minus sigma sigma transpose. Then they prove that if you look at the limit n to infinite of MMSE lambda, this is actually 1 if lambda is less than or equal to 1. That's below the information theoretic threshold. And it's some specific constant q star square if lambda is greater than 1. Right? And Q star is implicitly defined through a fixed point equation, so I won't get into that description. But this is just to say that we understand what is the base optimal performance. We have a benchmark so that moving forward, whenever we have some other estimator, we'll try to compare its performance to this benchmark. And not only under this MMSE, under this also correlation kind of metric, we know what the optimal overlaps are, things like that. Okay, any question so far on what we are trying to do? Yeah?
So the first two questions, detection and recovery, were binary questions, yes or no questions in some sense, right?
Right.
But here there is a metric. This limiting MMSE is, I don't know, it's either 1 or some number and some number smaller than 1.
Right.
How should I think of this metric? I mean,
yeah, so essentially it's saying that below the information theoretic threshold,
it's pretty bad.
You can't really do anything. There's a fundamental threshold. But then as lambda increases, your MMSE goes down to 0. And this Q star is a function of lambda. So this essentially tells us exactly how the MMSE decays as the SNR parameter lambda goes up.
Okay.
Right?
Is there a point at which, after which it is like actually 0?
No, it will decay smoothly.
Okay.
So in your basic formulations, do you put the kind of uniform prior on all possible?
For which one? So sigma has this distribution, right? The coordinates of sigma are +1 or -1 with probability half. So that's my prior essentially on the signal.
Do you assume that lambda is in the basic formulation? You will assume lambda is given, right? Okay.
Yeah, lambda is a fixed constant that's positive and it's known and it's independent of n. Okay.
So if the Q star, is that limiting thing continuous at 1? If lambda is slightly more?
Yeah. So if you look at the MMSE, the limiting MMSE, yeah, at least for this problem, you don't have a drastic jump. It's, I think, like this, up to 1, and then it decays. Okay. So the main question for us is, can we have, let's say, efficient estimators that attain base optimal performance? Right. And the main challenge, of course, is that you could say, well, I can always calculate my base optimal estimator. Note that this involves this, high dimensional sum over the corners of the hypercube. So this is not really computationally feasible. We can't really compute this in practice. So we have this question, do we have efficient estimators that are base optimal? Okay. And I'll mainly talk about two different classes of estimators which have been very recently established to be, provably base optimal, at least for this example. So two classes of strategies. The first is approximate message passing. And the second is variational inference. And allied methods, let's say. So these are actually slightly different from the methods that we have seen so far. As we'll see, approximate message passing, or AMP. This is an iterative algorithm, so it's still cheap, but it's not like an SDP or a spectral algorithm that we have seen, but it's still kind of vector matrix products along with some nonlinearities. We'll look at this algorithm in depth. And then variational inference and these algorithms, these essentially are non-convex algorithms. So they actually set up a non-convex loss function and they essentially try to optimize it. So there is now proof that you can actually optimize even these non-convex objectives in this setting, and they lead to good statistical performance. But I wanted to kind of emphasize that in terms of algorithmic paradigms, these are slightly different from what we have seen so far. Okay, so let me talk about approximate message passing. So this class of methods actually originally came up, they were formally proven, let me say, just by Baiati and Montanari, but they had come up even earlier in the work of Donohoe, Malecki, and Montanari in the context of compressed sensing back around 2011. But most of the results that I'll talk about are actually from a much more recent paper by Montanari and Venkatramanan. That's from 2019. And there's an even more recent result that I'll quote at some point. But without getting too much into it right away, let me just first describe the algorithm completely. So what is this algorithm? So the algorithm is, so to define the algorithm, I will need phi1, which is the unit norm top eigenvector of M. And then the algorithm has two steps. The first is, an initialization, where you set a vector x0 to be square root n phi1, and then an iteration step where xt plus 1 is the matrix M times ft xt minus bt times ft minus 1 xt minus 1, where bt is 1 over n sum I from 1 to n ft prime at xt xti. Okay, so let me parse this algorithm. Turns out it's not one algorithm, but rather a class of algorithms. But what are we doing? So this is an iterative algorithm, so we maintain this set of iterates xt. Each is a vector in Rn. Okay, so I initialize it with x0, which is just a scaled version of my top eigenvector. That's fine. Now what do I do? So at each step, ft is actually just a function on the real line. Okay, so when I talk about ft of xt, what I mean is that I apply the function ft coordinate wise. I mixed up my subscripts and superscripts. This is xt. So ft of xt is just ft xt1 ft xtn. Okay, so this is still a vector. I just take my iterate at time t, I apply the nonlinearity ft coordinate wise, I get a new vector, I apply the matrix M to it, and then I have this term that I subtract off, which I'll explain in a bit. which is this constant bt. This is just the average of ft prime. And then, ft minus 1 applied to xt minus 1. This is again coordinate-wise nonlinearity. Right? So this is a sequence of vectors that I obtain. And this is not one algorithm in the sense that for every possible choice of these nonlinearities ft, I get a different instance of this algorithm. And it will be up to the algorithm designer to actually choose what nonlinearities to use at each step. Okay, any questions about just the structure of the algorithm?
So bt is ft prime.
Yeah, so the derivative of ft, so for our discussion, imagine it's like a smooth function and all. So this is the derivative of ft applied to the coordinates of xt, and then I take an average.
Are you going to give us examples of these ft's?
Yeah, so I'll talk at length about why this algorithm is coming up, sort of what is some intuition for this. Okay. Okay. So so why would you even want to do an algorithm of this form, right? The heuristics.
Oh, what is the output?
Yeah, so the output is just, you keep running this xt's, and right, so what is your output? So let's say, yeah, good. I want to check one thing.
We still want a matrix, right?
No, this will give you, okay, right, great question. So this will give you a vector so that you can measure its performance using a correlation. Or if you want a matrix, then you can look at the rank 1 outer product of that vector. And the output is that, if you run it for some t iterations, then you define your x hat t to be basically ft of xt divided by lambda. So you run this iteration for some big T number of steps, and then this is your output. Okay. Good. And exactly as Shiva mentioned, if you want to just measure the correlation, you can do it directly using this output. If you want a rank 1 matrix, you can look at its outer product. This will be your estimate. Okay, so why is this something reasonable, right? So for the moment, suppose in addition to m, we also have a vector y, which follows normal with a mean mu naught times sigma, and sorry for the conflicting notation, I hope this is clear. So what I mean here is that in addition to the matrix M, you have this underlying vector sigma that you're really interested in, right? So what I'm imagining here is that you have this side information, let's say, where the ith coordinate is basically some mean times the ith coordinate of sigma plus some scalar sigma naught times a Gaussian. Okay, so suppose you have this additional information given to you. Of course, if you only had access to y, and if you needed to do inference on sigma, we know what to do, right? You would apply a coordinate-wise nonlinearity. If you just had your sigma hat based on y, would be this vector that you get by applying a function coordinate-wise to yi, right? And this function of x would be basically the expectation of sigma given mu naught sigma plus sigma naught times z. Right? This would be your posterior mean denoiser. Just by Bayes' rule, this would be the best estimate that you have if you just had access to y. right? But now you can say, well, this is, I mean, of course, I still have my matrix M, right? That contains a lot of information. And if I just wanted to do this, then I didn't really use any information from M, right? Of course, if I can extract some information about sigma from M, I should be doing better. So what you can do here is that you can construct a first level estimator x1, let's say, which is like M, let me call this denoiser f0, times f0 of y. Right. Okay. So if you hit the matrix M with this f0 of y, which is your best estimate given just the side information, if you expand it out in terms of what the matrix M is, this will exactly be lambda over n, inner product of sigma and f0 of y times sigma, and plus the Gaussian matrix times f0 of y. Okay. So I haven't done anything, I've just expanded it out in terms of the matrix M. Right? There is a rank 1 spike, this leads to the first term, there is a noise term. Okay. And now, if you look at this, you immediately see because this little y is independent of M, this term is basically a normal vector with mean 0 and a variance that is norm of f naught y square over n. That's the distribution of each coordinate in this vector, right? So this times n. And if you look at this particular term, okay, this is like an IID sum, right? Because sigma I, yi is just a function of sigma I. So this one is just an IID sum. So if you now divide by n, that's like taking an IID average. So this term will essentially concentrate around a fixed number. Okay? And so if you look at the vector x1, this actually follows normal with a mean which is mu1 of sigma and some variance where mu1 is what I would get from this constant average. So it's lambda times the expectation of sigma naught f0 of mu naught sigma naught plus sigma 0 g, and sigma 1 squared is expectation f0 of mu naught sigma naught right? So where sigma naught is Rademacher, G is Gaussian, and these are independent. Okay, and this is essentially coming exactly from this description, right? This variance, this is an average. This will essentially converge to this particular constant. And then the mean here will essentially converge to mu1. Okay, any questions so far?
What is the sigma naught?
So sigma naught is a dummy for this empirical coordinate from this little sigma, right? So sigma naught itself is a random variable, which is either +1 or -1.
But is it independent of?
So I don't need it to be independent of something. Here it just appears through its expectations, right? So I just need these numbers. So all I'm trying to do is express this empirical average, let's say. It will come out in terms of some limit. So what will that limit be? Because every coordinate of f, y I is basically this quantity. So if I evaluate the expectation, I will just get something here in terms of a Gaussian and a ±1 random variable. That's all that I'm writing. Okay.
I guess I'm worried about, if I look at x1, there's a sigma inside the inner product, there's a sigma outside.
Yeah.
And they're the same thing. Now, are we saying that we're replacing the inner sigma with the sigma?
Well, I'm just saying that if I look at 1 over n sigma f naught y, I'm saying that this converges to a number, almost surely, which is mu1. And I'm just saying that the limit mu1 is just this number. And the other thing I'm saying is that if I look at f0 of y square on n, that converges almost surely to sigma 1 squared. Okay. So there is something nice at least about this thing, right? If you have this side information, there is something really nice that happened. If you started with a vector that is like some mean times sigma plus some variance, if you do this operation, you end up with something that is still a mean times a Gaussian plus some other variance, right? Okay. And so this would lead you naturally to this idea where you would say, okay, let me just keep iterating this, right? Maybe I take x1, I hit it again with m, and then I look at its distribution and I keep getting a new sequence of iterative estimators, right? So this would lead to this naive idea that like, okay, why don't I keep iterating this system? And you're at least clear at the very first step that you had some information just from y. When you hit it with m, you definitely gained, right? Because you got this inner product, which also is a function of sigma. So you extracted some information out of m. So you would naturally expect if I can continue doing this, I can potentially keep boosting my SNR. And maybe that will be already good enough. That's sort of the idea. The issue, however, is that just this naive algorithm kind of, this naive justification kind of gets stuck beyond this first iteration. The idea is that, of course, now if you try to write down x2, that will be m times, some new nonlinearity f1 applied to x1. And you know what is the best nonlinearity to apply to x1 given this distribution. But the issue is that x1 is actually itself a function of m, right? So now things start becoming correlated. It is no longer true. The difficulty is that, let's say if I look at x2 is not some normal with mu2 sigma and sigma 2 squared identity, naturally. And that happens because you now start looking at m at every step, and you have some correlation that starts coming up. Right? Okay. Okay, so this is where essentially AMP comes to the rescue. The whole point of this additional term that you subtract out is to essentially kill these dependencies so that in an appropriate sense, which I'll make precise in a moment, this Gaussian description is still true for any higher iteration. Okay? To ensure that, this is exactly why we need this additional term. And this is what really sets it apart from something like power iteration. This term is often referred to as the Onsager term. But this is sort of its main motivation. Okay. So let me state what I mean when I say that if you look at AMP in an appropriate sense, this Gaussian distribution still remains true after arbitrarily many rounds. Where do I write it? Let me write it here.
So before you move on, can you explain
what happens if t is linear? I know you emphasize non-linear. So
yeah, I mean, right. So if you have some linear function of the yi's, let's say c times yi, right? You can calculate what the corresponding mu1 and sigma 1 square will be. But beyond that, you can't really do anything much here, right? And it's clear that if you apply a better function f here, then if you try to estimate sigma based on x1, you will be able to do better in terms of mean square error, right? So we're just trying to find what is the best denoiser in this problem, at least so far. Okay, so here is a theorem. Okay, let me state it. So theorems of this flavor in the context of approximate message passing, they're often referred to as state evolution results. What do they say? Okay, so first we assume that lambda is bigger than 1. That's fine, we are above the information theoretic threshold. And without loss of generality, we assume that this is non-negative, right? If it is negative, we just have to flip the sign. So we can always assume this is non-negative. Now let ft be a sequence of maps from R to R. And let's say these are Lipschitz for any t bigger than 1. Now I define a sequence mu t sigma t recursively. So mu naught is sigma naught 1 over lambda, and then mu t plus 1 is lambda times the expectation of sigma naught times ft mu t of sigma naught plus sigma t times g. So sigma naught and g are exactly as I described before, two independent variables. One is plus minus 1, one is a Gaussian. And sigma t plus 1 squared is the expectation of ft times mu t sigma naught plus sigma t g squared. So this looks very much similar to how we obtained mu1 and sigma 1 square from mu naught and sigma naught. Right? It's a very similar update scheme. But this is just, a scalar recursion, a two-dimensional recursion. I can start from mu naught sigma naught and I can keep updating it to get this set of numbers. The main conclusion is the following. So suppose I have a bivariate function psi satisfying, okay, there are some conditions, I'll state them in a bit, but for the moment, the main conclusion of this result is that if I look at this quantity, okay, let's look at it together for a bit, right? So what is the main result saying here, right? It's saying that suppose I take a sequence of nonlinearities ft, okay? These are Lipschitz, so these are smooth, let's say. Forget complications on ft. These are really nice functions. I can get these parameters mu and sigma just by doing this scalar two-dimensional recursion. I start from mu 0, sigma 0. I calculate what is mu 1, sigma 1 square. I calculate what is mu 2, sigma 2 square, and so on and so forth. Then this is essentially saying that if I look at the empirical average of sigma I and xi t, it's essentially given by this expectation applied to psi, right? So if you see, this is roughly an analog of this statement, right? For example, if I had a vector that was exactly an n-dimensional multivariate Gaussian, then if I looked at empirical averages or the empirical distribution, let's say of x1t or x1i, this would basically converge to the expectation of f of mu1 times sigma naught plus sigma 1 times g. So this is an appropriate generalization of our discussion here. It's basically saying that if I look at the empirical distribution of sigma and xt, then it's actually a given bivariate distribution. If I look at the marginal of xt, then it's basically like mu t times, the mean plus sigma t times a Gaussian. That's basically what it is saying, right? So it's a generalization of what we had in our heuristic discussion. This is a strengthening because, okay, it doesn't use any side information whatsoever. It starts from a data-dependent initialization, and it's weaker only in that it doesn't directly say that xt itself has a certain distribution. Rather, it's saying that if I look at the empirical distribution of xt, then it has this particular form. Okay. Let me know if there are any questions. Let me pause here for a bit. And okay, I need some conditions on psi. Psi basically is like a Lipschitz function, but it's a bit weaker. But let me not state that exact condition. So for all kind of nice function psi that you can think of, this is really what is going on.
What is sigma 0?
Sigma 0 again is my proxy. Sorry, which sigma 0?
Capital sigma 0.
Right. Sorry for the notational overload. So sigma and g again have this distribution here that I described.
Okay.
Right. So sigma naught is again a Rademacher variable. G is a Gaussian, and these two are independent.
Oh, the sigma I in that statement is the original sigma.
This sigma I is this original sigma I.
This function, is this a fixed function? Or
This is for any class of, for any function psi which satisfies some growth conditions. So not for a fixed function, for any test function. This is really saying that if you look at the empirical distribution, it's converging to this thing in some Wasserstein kind of distance. But roughly to say, okay, so to show an application of this, right? Like, why do I care about this result? Let me talk about one specific example, and I think that will be helpful.
Can I ask one question?
Sure.
So the idea that you're trying to convey is that this xit time t is kind of normal.
It is like this mean times, the signal plus normal. That's really what I'm trying to communicate.
Yes. So for normal you need only two moments. So
Okay.
here, if you show first and second moment of xit is kind of matches with that of normal. You predicted normal.
That it won't be enough, right? Like if I know a random variable has the same first two moments as a Gaussian, it's not necessarily normal, right?
Yeah, but then how this is implying that it is normal? It is kind of normal.
Okay, so let me do one example. Maybe that will be helpful, right? So what I mean by this is that, for example, as an application, for example, if I take psi of x and y to be just the product function xy, right? Then this tells me that if I look at 1 over n psi of sigma I xit, this will be this will converge to the expectation of sigma naught times mu t times sigma naught plus sigma t times g, right? Which is exactly mu t, right? And then if I look at what should I look at? Yeah, so for example, the main point of this entire thing is that if for a specific choice of ft's, you get a particular estimator for little sigma I, right? And this is exactly now, if you look at this, this is 1 over n sum I from 1 to n, sigma I times xit. So this is basically exactly related to the correlation that you obtain. So you can exactly characterize what correlation you obtain in terms of this scalar recursion sequence, right? So this is, you know, the analogy that I wish to convey is exactly up to this sense, that if you calculate these averages involving sigma I and xit, you can exactly calculate these limiting correlations or such functionals in terms of the scalar recursions. Okay? And therefore now you see that as an algorithm designer, your task, or you know, basically the question is, what is my best choice of ft? Can I choose a good sequence of ft's such that my statistical performance is optimized? The power of this result is that it doesn't care what sequence of ft's you use. You can use a bad sequence of ft's, you'll get a very bad estimator, but you can still track its performance. So once you have this, you can now try to go ahead and optimize your choice of ft's, your choice of nonlinearities, and therefore get a good estimator out of this.
Question.
Yeah.
So you had that intuition where you started with the side information.
Yeah.
And then we had the issue of the correlations, right? If you wanted to iterate. So this theorem is saying that forget about side information, forget about correlations, everything else.
Yeah.
There is true. That's what this is saying.
Right.
Okay.
And this is essentially from, I mean, the intuition to go essentially from the heuristic step to the formal result is that if you have lambda bigger than 1, if you look at the top eigenvector, that is like the side information. So you can already extract it.
Except that it has correlations,
with
but we're correcting that with the beta.
With the term that you subtract off. So it's essentially like, yeah, so at each step you keep track of the correlation that accumulates and you keep subtracting it. Right, but this is sort of the main point. And okay, so let me state a positive result. This is the main upshot. This is the main upshot of, yes?
What is the machinery used to prove the result?
Yeah, so there is a fair amount of machinery which goes into this. But the main, one of the critical ideas that originally came from the work of Erwin Bolthausen and later was used by Bhayati Montanari, and there has been a very long line of work following up on these, but the main idea is to actually use a Gaussian conditioning trick. So you basically realize that if you have run your algorithm for t steps, then the correlation that has accumulated is basically like linear projections of your Gaussian matrix for t steps. So you basically condition on that, and then you look at, you know, you write down your noise matrix as whatever you had so far plus an independent Gaussian, and then you kind of recursively and iteratively keep tracking of, you know, how these things evolve. And that essentially directly leads to this scalar recursion, and then things kind of happen. But okay, there's a fair amount of
Last question.
yeah.
So you said this is called approximate message passing. Where does that terminology come from? I'm familiar with message passing.
Right. So typically message passing happens on graphs, right? But if you look at the corresponding analog of the graph here, okay. Message passing, vanilla message passing happens on graphs and is used to calculate like marginals of distributions indexed by graphs or something, right? And if the graph is a tree, then message passing is exact. People expect that if the graph is not a tree but locally like a tree, so if the loops are very large, then it's still giving you approximate, correct things roughly. But here the situation is actually very different. If you write down the corresponding graph, it's actually not even locally tree-like. It's actually a complete graph. So it's very dense. And if you try to do message passing on these graphs, it's totally unclear. A priori, it's totally unclear what will happen. But turns out that in this case, there is a CLT kind of effect that happens. You have some averaging because you have, each vertex has degree which is of order n, and the edges are basically have weights which is 1 over root n. So you have some central limit kind of effect happening, and that's why these algorithms are approximate message passing algorithms.
Okay, so the multiplying by m is like this message passing step.
Yeah, exactly. That's in the context of graphs, you would multiply by the adjacency matrix. Yeah, that would be the averaging step. This is sort of the approximate version of that. Sorry, we went off on a tangent, but this is the formal result. Okay, and the result of Montanari and Venkataramanan from 2019 that I really want to emphasize is that if lambda is bigger than 1, I'll state it in a very informal way. But if lambda is bigger than 1, there exists an optimal choice of the nonlinearities ft such that if I look at the estimator x hat t, which is ft of xt, this is approximately Bayes optimal. That is, if you do, so if you look at the expectation of x hat t transpose minus sigma sigma transpose Frobenius norm squared 1 over n square. If you look at it in the double limit, this converges to, or this is equal to MMSE, let me say it in this form, limit where MMSE lambda was the Bayes optimal performance that we had stated earlier, right? So what they are saying essentially is that you can choose your nonlinearities ft in this problem appropriately and cleverly, so that once you have this choice, your estimator is approximately Bayes optimal in this iterated sense. Okay? So first you take n going off to infinity, and then you take t to infinity. In this sense, it attains the optimal, Bayes optimal error. So, main takeaway, you can choose your nonlinearities appropriately so that approximate message passing will give you a Bayes optimal estimator. That's the main punchline here. There is a small wrinkle in this argument which you might complain about, which is this double limit. You might say, okay, ideally I want to take my limit t to infinity before I take my limit n to infinity. And it's actually a recent result due to Gen, Lee, and Yuting Wei from earlier this year that you can actually do this. So you don't really even care that you are running this algorithm for a fixed number of steps. You can make t grow with n and attain the best, Bayes optimal error. So yeah, things are nice. At least in this problem, you can choose your nonlinearities appropriately to get Bayes optimal error. And this is one class of algorithms that can be helpful in these problems. Okay, let me.
Fixed t, do you have any error bound? Like how does it decay with t?
So I think this paper of Lee and Wei does this. I think they have this hammer, at least for this problem, to really understand what's going on, and their result is completely non-asymptotic, so I think they have this. But it's very recent, so, but yeah, I think now there is an understanding of this, at least for this problem, okay? Okay, so I think this is a good time to maybe pause for a bit, and then we'll come back, and in the meantime, let me know if there are more questions on this. Once we come back, I want to talk a bit about the variational strategy. The second class of algorithms that I want to talk about, which furnish Bayes optimal estimators in this particular context, is related to the strategy of variational inference. And as we'll see, it will essentially reduce to a problem of non-convex optimization. Okay, so the idea is as follows, right? Roughly, so if we are trying to estimate this rank 1 matrix sigma sigma transpose, right, then our best estimate x hat Bayes is exactly the posterior expectation of this rank 1 matrix given our data, right? Now this is an n by n symmetric matrix. If you look at its ijth entry, that's basically just the expectation of sigma I sigma j given n. Okay? So to essentially get a good handle on x hat Bayes, we need just the two-dimensional marginals, right? To calculate this expectation, I don't need to know the entire posterior distribution. I just need the two-dimensional marginals. Or let's say some low-dimensional marginals of the posterior distribution. And so one idea would be to say, okay, first let's write down what is the posterior distribution. This this one can just check by Bayes' rule that this is basically some normalizing constant times e to the, I think, lambda. Let me use V here. V transpose MV. Right. So this distribution is kind of still a bit intractable, right? Because I have this normalizing constant z that I don't really, I can't really work with. So I can't really sample from this distribution per se. It's not clear that I can easily sample from this and calculate these bivariate expectations. But you can look at it and say, well, maybe the low-dimensional distributions of this, high-dimensional posterior are roughly independent. So if I need access to low-dimensional marginals, maybe I can forget the dependence among the coordinates, and maybe I'll be okay, right? So this leads to this idea of variational inference. Where you try to get a good approximation to your posterior by minimizing the KL divergence between Q and P. This is your posterior. And you do this minimization over a certain class of distributions, right? And the most popular choice is this class of product distributions. So every coordinate is independent. And this strategy is usually referred to as naive mean field. Or NMF. Okay, so what strategy are we talking about? If we want to do naive mean field for this problem, we say, well, let's say I can solve this optimization problem over the set of product distributions. I would get Qi hat, or Qi hat would be some, so let's say my optimizer is a product distribution, Qi hat. Then I can take Qi hat, Qj hat, I can assume they are independent, I can calculate this for every I and j, that would give me some estimate, right? That would be the naive mean field estimator for this, right? And okay, your question would then be, fine, if I want to put this strategy to practice, I actually need to solve this optimization problem, so I need to calculate what is this KL divergence. So turns out that if you have any product distribution, of course, on the hypercube, so if each Qi is supported on -1 and 1, any such distribution is, of course, exactly described by just its mean, right? If I have a distribution that's supported on -1 and 1, if I tell you what the mean mi is, then you know exactly what this distribution is. And then the KL divergence of Q and P, this turns out to just be some function of m. M is the vector plus some constant that we don't really care about, where f of m is negative lambda over 2 m m0 m minus sum I from 1 to m n h of mi, where h is the binary entropy. So it's negative 1 plus x log. Sorry, any questions?
Sorry, I missed what little m was.
Little m is this vector of means. So I'm saying that if you give me a product distribution, then I just need to tell you what each component is. Each component is a distribution on negative 1, 1. So it can be described by its one-dimensional mean. So in fact, each q is completely in one-to-one correspondence with the vector of means, right? And in this case, if we write down what the KL divergence is, it can be expressed exactly in terms of the mean vector. So I just want to say that this KL divergence minimization problem, at least in this case, reduces to a scalar optimization problem, although a high-dimensional one, right? So this problem is basically now just the minimization over m of f of m, the equivalent, right? And sorry, one small thing, this m0 is nothing but m minus its diagonal. So you need to subtract out the diagonal. This doesn't really make a big difference. I missed these factors. Okay. So this would be the naive mean field strategy in this problem, right? We set up this optimization problem over the solid hypercube. This function fm generally doesn't have any nice structure such as convexity or something, but it's a continuous problem. And if you believed this heuristic, you would start, you would get some initialization. You would run maybe something like gradient descent on fm. You would get m. Once you get m, you know what the qi's are, and we can then calculate what this function would be. That would be the strategy.
What's capital M 0? Oh, sorry.
Yeah, that's just, I need to remove the diagonals of m. But you can put m there as well. Asymptotically, won't change anything.
Sorry, is this convex?
No. The entropy term is nice. The quadratic form doesn't have any. Yeah, so there's a bunch of questions, right? Like, does solving this give you anything meaningful statistically? Can you actually optimize it? So there's two kind of questions here. There's an optimization angle, there's a statistical angle. Okay. Now, after all this build up, we'll have a temporary setback when I'll tell you that actually in this problem, this particular strategy will not give you anything meaningful, or is expected not to give you something quite meaningful. And actually, I mean, you can kind of see that already at a certain level. So this particular evidence for this actually came up in this paper by Gorbani, May and Montanari in 2018. So they said, fine, let's look at the regime. Let's fix some lambda strictly less than 1, right? We know this is the regime below the information theoretic threshold. So in this case, no estimator can have non-trivial correlations with the planted truth, so with the vector sigma, right? So in fact, therefore, if you look at the posterior distribution, roughly all the coordinates should be uniform. And you should therefore have m star equals 0 should be at least a local minimizer. Right? Because that's what you expect the right answer to be. So if you started at m star, you should stay at m star, at least. That's a baseline requirement. But turns out, okay, so one thing is true. If you look at the gradient of f at m star is 0, this is always 0. So at least it's a stationary point. That's fine. But if you look at the function, the Hessian of f, this is negative lambda m naught plus identity. So I just took the Hessian here. But we can analyze this matrix really well, right? Because m0 is basically our spiked Gaussian matrix. We understand its spectrum really well. And so in fact, it turns out that if you look at the lambda min of the Hessian at m star is 0, this is 1 minus 2 lambda if lambda is less than 1, and this is negative lambda squared if lambda is bigger than 1. So for m star equals 0 to be a local minimum, you want this to be positive. But this is positive only if lambda is less than a half, right? So 1 minus 2 lambda is positive if and only if lambda is less than a half, right? So in fact, if you are in this regime, lambda half to 1, this is already something weird that is happening, right? So m star 0 is actually not a local minimum in this regime. So in fact, what it suggests is that if you use the naive mean field strategy in this particular problem, if you are in this regime between half and 1, even if you start at 0, 0 will actually end up being a saddle point, so you'll escape 0. And this algorithm will give you wrong predictions, and not only that, it will give you wrong predictions with a lot of accuracy, which is kind of the worst of both worlds. Okay, so we can kind of see that, but okay, there is still something a bit subtle here which I want to point out, which is you might say, okay, this is talking about the regime lambda less than 1. I actually care about lambda bigger than 1 where this is still okay. And actually, we still don't quite know what happens if you do this strategy for lambda bigger than 1. That's actually not understood. What is understood, however, is that I think we would believe, okay, I don't have a lot of confidence on this, but I think the belief is that if you followed this strategy for lambda bigger than 1, you would do weak recovery, but I'm not quite sure if it would be Bayes optimal. But okay, so what is the fix to this? Can we fix this? So the idea is that the candidate now, so what you say is that I had some function f. Instead of considering that function, I'll come up with a new objective function, which is basically like negative lambda on 2n, m big M little m, minus 1 on n, sum I from 1 to n, h of mi, and minus lambda squared on 4, 1 minus q of m squared, where q of m is basically the L2 norm of m square over n. Okay, so a few remarks. One is that the function f tap is basically this function f, if I forget the last term, up to a scaling by n. Right? That's okay. I've changed the diagonal entries because once I divide by n, this diagonal doesn't really play a big role, so I can remove that. The main surprise here is this additional term that we added. So this particular form of the function, this actually comes from a long line of heuristic or non-rigorous results in statistical physics, but which are extremely deep and sophisticated. So the TAP here stands for Thales, Anderson, and Palmer. Three very, very well-renowned statistical physicists who looked at these problems in the context of some non-crystalline materials originally in statistical physics back in the late 70s and 80s. Turns out the same kind of heuristics are also useful if you look at high-dimensional statistics models, and especially posterior distributions coming out of high-dimensional probability distributions or statistical models. So the strategy in this case is the same, just that we will change from the function fm to ftap. The conjecture is that now if you take this new function, this is still not convex or anything, but if you start with a good initialization and if you run gradient descent or something, you should get an optimizer that has good statistical performance and in fact is Bayes optimal. That's the conjecture. Okay? And in fact, this is no longer just a conjecture, we have proofs now. So this is a very recent line of work. This was actually started by Fan Mei and Montanari in 2020, and then there is a more recent result by Celentano, Fan, MA, which is from a year ago. Okay, and I'll state this result informally. But the result essentially is that you fix any lambda bigger than 1, right? Then there exists a local minimizer m star such that 1 over n m star transpose minus x hat base okay. So you're basically calculating the Bayes optimal estimator if you can get to this minimizer. So this is the statistical result. The next parts of this result are essentially algorithmic or of an optimization theoretic flavor, and they say that FTAP is strongly convex in an square root epsilon n neighborhood of m star. Okay, so roughly there is a good local minimizer, and the function is well behaved in a local neighborhood of this minimizer. So if you actually ended up there, then if you do gradient descent or natural gradient descent, you will end up at this minimizer. And the third is a rate result, which essentially says that if you start with spectral initialization plus some constant rounds of AMP, so this first part of the algorithm will give you, will land you in this square root epsilon n neighborhood, and then do mirror descent on FTAP. This will give you a linear convergence rate to m star. So this result, this is coming from a set of papers, but the result actually answers all the questions that you might want. There is the first part, which is essentially saying that there is a good local optimizer which has optimal statistical performance, and you can get it essentially by a good initialization that lands you in a small neighborhood around m star, and then doing some kind of gradient descent procedure. Yeah.
When you say constant rounds of AMP, what FT do you use there?
So so it's essentially the same choice that I mentioned in the context of AMP. The optimal denoisers, basically. Yeah, so they did it in this way because they were not relying on this result of Lee and Wei, so they could only run AMP for finitely many rounds. That's what they could analyze. But even if with a constant number of iterations, you could get into this square root epsilon n neighborhood. That one could prove. And so the formal result here is that you start with some warm start, then you boost it up to a point, and then if you do some gradient descent, you get to the optimum.
But why do you need this if you're doing AMP anyway? We know it works.
Yeah, so right. So the result that you can run AMP for a diverging number of steps and still have the same state evolution guarantee came later. Formally, for the longest time, what we have been able to analyze is the performance of AMP run for a constant number of steps. And if you run it only for a constant number of steps, then you get arbitrarily close to Bayes optimal performance, but it's not clear you're actually solving the Bayes problem at finite n. Okay.
One more question. So that 1 minus QM is important, basically. That's the main message, right?
That's the main message. That's kind of the magic that happens here. And it's actually very closely related to sort of the term that I subtracted out of AMP. I mean, these two strategies actually are coming from the same perspective in some sense.
Oh, the B term,
The Onsager term. These are roughly related, and it's the same kind of correction. This is in the same correction dressed up in a new light. But effectively, it's the same thing that's happening. And but there are certain subtleties here. For example, if we pause to think about it, there is still something that's subtle here. For example, this is true, and one can prove this, that if you actually look at the low-dimensional marginals of the posterior, these are approximately independent. So if you look at the distribution of the ith variable and the jth variable in the posterior, in the limit, these are independent. This is true. However, if I use the naive mean field approximation, somehow that still doesn't give me the right thing. And this is because of some implicit dependence among all the variables that somehow still has a role to play. And this correction term somehow adjusts for it, but it's a bit implicit. Okay. Right. So I should say that I started today's discussion saying that we are interested in optimal recovery, and then I spent all this time just talking about one model. And that's essentially because our progress on the optimal recovery front is still kind of restricted to a few models that we understand really well. Okay? Especially in the context of problems with sparse graphs like community detection, we simply still don't have the tools to answer these questions. So the only paper I know, so there is a paper by Jiaming Zhu and Elkanan Mosel from 2016, I think, that talks about optimal recovery for community detection. But this paper deals with block model graphs that are much more dense on average. So the degrees are diverging and they are growing at a certain rate. So truly sparse graphs are still difficult and beyond our reach. Okay? But at least in these Gaussian-ish examples, we have some results that are emerging in recent times. And I kind of grounded this entire discussion in the context of the Z2 synchronization problem, which is an unsupervised problem. But you can ask a similar question also for supervised settings. And there, okay, we also have some emerging evidence. But yeah, this is, I think, sort of the state of the art in this area. Okay. How am I doing on time? Okay, good. Let me take the next 10-15 minutes and talk about computational gaps. Any questions before we move on?
So in AMP, you have a theorem saying that if you do the right FT, it works.
Yeah.
In practice, is there any do people use AMP in practice? If so, what FT do they?
Okay, that's a very hard question to answer. I think people who have been developing the theory here, I think there is strong evidence that if you use AMP, then you do well, even in practice. I think the settings where AMP has found very successful applications are in signal processing, particularly in the context of compressed sensing. That's actually one of the original places where these algorithms came up, and they really show very good practical performance, even with practical sensing matrices and decoders. And that's sort of one application where it's really necessary, because you can't really implement convex optimization based strategies on very large instances. These are really cheap algorithms. Okay, but now I think the second half of your question is, okay, to get optimal performance, I need optimal denoisers. And to get optimal denoisers, I need to know what kind of signal I'm working with. That's a harder question, but I think people have also looked at it. So there is a second half of this question, which is, can I actually, let's say I didn't know the distribution of the sigma entries, right? If they were, let's say, IID from some distribution, and I didn't know what these distributions were, Turns out in certain cases you can also learn that from the data. And then you can kind of plug these back in. So there's some empirical based kind of approaches that have been introduced in this context. So I think this is a rich area, and I think in the settings where these have been applied, they show really good performance. Okay.
In the naive mean field, the class that you took is this product distribution, right?
Right.
So is there any other richer class that has been considered?
So I think the difficulty here, and this is something I've been wondering about quite a lot as well. I think the issue is if you try, so there are two ways to go, right? One is you can say instead of doing naive mean field, I'll still do I'll do approximations by something, but I'll assume a richer class. Or you could try to change the objective function, as in this approach. The thing that is not clear, the thing that kind of becomes an issue is that if you change the class of distributions, then the optimization step becomes much more complicated. Here, one of the big advantages was that we could reduce ourselves to the mean space, and instead of doing optimization on the space of probability distributions, we could do it on some scalar problem. Still high dimensional, but at least a scalar problem. That is not true in general once you move beyond these product classes. That essentially causes a lot of pain. Okay, so let me take maybe a few minutes to talk about computational statistical gaps, because I think if I don't mention this at all, it will leave this discussion very incomplete. So over the past 2 or 3 lectures, we've been talking about recovery and detection and optimal recovery and so on and so forth. But in whatever examples we have discussed so far, when detection is possible, we have had very efficient algorithms as well. Spectral algorithms, semi-definite programs, iterative methods, non-convex optimization with provable guarantees. Everything has been nice. When you can recover them, you can also recover them in efficient time. Turns out there is an additional wrinkle here the moment you move beyond these simple examples, right? So the broad question that I would like to pose here is detection or weak recovery always possible using efficient algorithms? Right? And let me give you one very stark example, which is a very small generalization of our community detection problem, but now with K groups. Community detection with K groups. So the idea here is that I fix some K which is strictly bigger than 2. Let's say bigger than or equal to 2. Now my sigma i's are IID uniform on 1 to K, and my probability of having an edge so this is exactly the problem we've seen so far if we fix K equals 2. So I'm just talking about a variant of this for higher K. Right? So here, if I define the average degree, that's basically A plus K minus 1B on K. And one of the surprising, so one fact is that all existing algorithms for or existing polytime algorithms, let's say, polytime algorithms for detection and weak recovery. Require this quantity lambda, which is a minus b over square root k times a plus k minus 1 b, to be strictly bigger than 1. Okay? So again, the intuition is the same, right? If a and b are very different, the larger the difference between a and b, the easier this problem becomes. So far all the algorithms that have been analyzed for detection and weak recovery, they work as long as this parameter is bigger than 1. And of course, for k equals 2, we get back to the information theoretic threshold we have seen before. This threshold is known as the Keston-Stigum threshold. Stigum threshold. The surprising fact, so surprise, is that there is a result due to Emmanuel Abbé and Colin Sandon from a few years ago, where they show that if exponential budget available, then one can beat the KS threshold. All right. So in fact, if you had exponential computational budget, you can actually beat this threshold. You can go below, right? And in fact, the information theoretic threshold for this model, it has been worked out under this condition that B must be bigger than A. That's, I think, a technical requirement. It came up in the work of Amin Kojaoglan, Will Perkins, Lenka Zeborova, and Flora Karzkala from a few years ago. So the emerging picture is that, in terms of the difference between A and B, there is some lambda Ks, and there is some lambda IT, which should be strictly below, right? And so the entire question is what happens in this regime. And the emerging evidence seems to be, and there has been a lot of work over the past 5 to 7 years at the intersection of, statistics, machine learning, computer science, statistical physics, and so far the emerging evidence seems to be that there is something real happening here. So in fact, it is believed that in this regime, although detection and weak recovery are information theoretically possible, it should not be possible using any efficient polytime algorithm, right? And in fact, this should be the exact threshold at which things get stuck. And there has been, some emerging evidence for these phenomena. Okay, so how do you do this? You try to rule out large classes of algorithms, right, for detection, for weak recovery. You try to consider, let's say, a big class of hypothesis tests, and you try to prove, okay, they don't work. For weak recovery, let's say you look at a class of convex programs and you prove these don't work. You look at some other class of algorithms, you prove they don't work, and things like that. For example, you can have variants of AMP. You can try to analyze it, and you can, using the state evolution machinery, you can say that, okay, AMP will not work, and things like this, right? And there have been a lot of results here, and turns out that there is nothing special about community detection problems. Such things, such computationally hard phases are now supposed, we expect them to exist in many unsupervised and supervised problems. So you expect this in the context of, sparse PCA, you expect it in the context of Bayes regression with certain priors and things like that. Okay? So this seems to be a very broad phenomenon, and there has been a lot of work that has been happening. also by many people here at Georgia Tech, where there has been accumulating evidence, and it has been a very fast-growing area over the past few years. Okay. So let me stop there. If there's interest, I'm happy to talk about some of the emerging evidences in this regard tomorrow briefly. But otherwise, we'll talk about some directions which I think are also quite open in this area at the moment, and I feel would be very nice to have results on. Okay.
Yes, question.
Yes.
So how do you do this? How do you get a question string about? Does SDP will work?
Oh, so how do you do that? So the same strategies that I described of like counting walks and then doing robust projections, they work up to the Kestenstiegem threshold. The Gormans-Williamson type SDP that I described works up to that threshold. So all the known strategies that were working up to the IT threshold for the 2 case, if you generalize them, they work up to the Kestenstiegem.
How do the Abbas-Anton?
Yeah, so they look at this belief propagation algorithm. They look at a linearized version of it, and then they analyze what happens there.
Has there been any, like, I don't know, maybe this is very like speculative, but like, is there relations to any coloring problems for these ones? Is there a reason why people think are different, or like no?
Yeah, so this is essentially like a planted version of the coloring problem, right? So essentially, instead of me just trying to find a coloring in a random graph, there is some underlying coloring that someone has given me, and then I'm trying to find it, right? The questions are of a slightly different flavor, and Santosh and I were also talking about this. For example, in the context of purely random instances, you try to find the best possible thing, right? Largest independent set, and things like that. Here, the question is slightly different. Can you distinguish it? So we have had much more success with the detection questions. I think recovery bounds are still relatively limited. But yeah, so it's, I guess to answer your question, it's more like this is a planted version of these problems. So there's some superficial connections, but I guess the questions are slightly different.
Yeah, because in some sense, right, 2 coloring, I know have exact algorithm, right?
Right.
Yes. For 3 coloring, things become hard. Of course, here you are counting edges, right? And similarly, you could ask problems like max cut, or I want to partition my graph into 3 parts and maximize the number of edges.
So
like there, we don't understand it as good.
Right. So for example, the MLE for community detection essentially is like balanced bisection kind of algorithms, right? So, but even for the 2 community case, trying to do min bisection, worst case is hard, right? But now I think there is a lot of evidence that if it's min bisection on Erdos-Renyi, then there is an algorithm that will actually do it. So yeah, there is. So, but there has been actually some work in trying to connect worst case hardness results to these things. I think Guy Bressler and some other folks have been pushing that quite a lot. But I think this connection is also tricky because this is sort of an average case statement in some sense. So even making sense of it